everyone. In this video, I'm going to show you how you can work with real world networks using Python iGraph. I'm going to take one particular and very popular network, which is called Karate Club Network. And we will see how you can crunch it using Python iGraph and what are some very basic kind of analysis that you can do over such a network. Karate Club Network is very popular and also it has a very interesting story behind it. The idea was that it's a friendship network of people in a karate club, and then one fine day there was a conflict between the instructor and the manager, which led the club to split up into two parts, and those two parts sort of became two communities of people which is very clearly visible in that network. So Jakari was the scientist who observed this for the first time, and hence the network is called Zachary Karate Club. Let me show you a brief picture of how this network looks like. You can go to Google and search for the images, and this is one of the visualizations of the network on ResearchGate. So it's a network of roughly 34 people over here. Now, this is a simple visualization of the network. We are going to import this network into our collab notebook and work with it. Right, so you don't have to install anything if you don't know how which what kind of installation is required to run a Python code, etc. All that is not needed. I'm going to use a collab notebook, and that is pretty much sufficient for even graphs up to a few thousands of nodes, rather tens of thousands of nodes. I'm going to go to Google Colab. So to come here, you can actually just search for Google Colab on Google and then just click on the first link over here. And this brings you to the um, Google Colab. Now, all we want to do is create a new notebook. So you can click here on new notebook, or you can cancel it, go to file and then create a new notebook. It might take, yeah, it's there. Let me name this file as karate itself. So this is going to be our file here. And so before coding and working with Karate Network, we need to import a few essential libraries and essential classes. So one of them is iGraph. Now, iGraph doesn't come pre-installed with Python or here on Colab Notebook. So you need to write a small command and install it. And every time you run your notebook after disconnecting, you have to do this again. Basically, if you're working on it today and then you open the same code tomorrow, you'll have to again install it. If you are doing it on your own system, then you need not install it again and again. I'm going to install iGraph. It will take some time. So meanwhile it happens, we are also going to upload certain files here. So if you look at this icon, you can click on it and it shows what all files are available with which you can work. So we will figure out a file corresponding to Karate Club Network on internet and bring that here and see how can we crunch that. iGraph is one library you need. Another library which we are going to use is either PyCaro or Caro CFFI. So you need this library so that you can visualize the graph. I'm going to install this as well. And one more thing. So after they are installed, I'm just going to import iGraph as IG. So please note that if you run this command before installing iGraph, it will show you an error. IG here is simply an alias of iGraph. So I can write iGraph or IG, and I'm going to import one more thing from iGraph, which is the class graph. Now don't worry if you don't understand what a class is. So the idea is you can import this graph. So this graph over here, it's called a class, and you can use it for creating a lot of graphs, as you will see later. So that's all we need, and we are set up to import our graph here and work with that. So let's get the data set. Now, I simply don't want to look at this graph. I want to get that data set. I'll go here, and the very first link that you see is for the Connect project. This Connect project has a lot of data sets. So this is for the Karate Club, but otherwise also if you click on networks here, you will see a large number of networks. There are like thousands of networks that you can use for any kind of project or any kind of research. And there are different kinds of networks. There are undirected, directed, bipartite, timestamp networks, so on and so forth. But right now we are going to work with this Karate Club network, and it says dataset is available for download. So you can read about this network a bit from here, and I'm going to download this dataset by clicking on this. It's the third time I'm downloading this file, so that's why it shows you. So if I go to downloads, it shows you a 3 written over here. So for you, it won't be there. I'm just going to extract it so that I can show you what is inside this zip folder. When you click on this, there are 3 files. So one is the README file. You can easily open all of these files in any editor. So Notepad for Windows or gedit for Linux, and you can read about again this data set here. You can find some more information here. It also tells you what are the other data sets, other files which are available. The one file is the metadata, and our main file, which is out.uci data, it contains 2 columns. So your first column is the ID of the from node, and second column is the ID of the to node. So basically, which are the 2 nodes along which relationship exists. And here is something important. So if for some reasons you are using this network into any kind of project or any kind of paper for or for some kind of testing, you should cite the following references. It is it's an ethical practice in research that you should follow. Right, so this data set basically comes from these places and you should cite them. So this was our first file, and metadata file contains some metadata. You can look at it, but our major file is this out file, and this is how your file looks like. So it is telling you that your graph is undirected, it is unweighted, and it has 78 nodes and some edges. 34 it has 34 nodes and 78 edges. We can check for that. And from third line onwards, you can see these are the relationships that exist. So from node 1 to 2, 1 to 3, 2 to 3, etc, etc. Right, so now we need to import, we need to get this file into our collab notebook so that we can start working with it. I'm going to click on this upload button here, and let's get this third file here. So just for keeping it quick, I'm going to rename this file, and I'm simply renaming this whole file as karate. That's all. So we have a file karate available with us, which we can use. Okay. Now coming back here, so we need to do a little bit of data pre-processing here. In the next video, I will show you another kind of graphs which can be directly imported. But here in this particular case, we need to pre-process the data. So let's see what that means. So the idea is whenever you are creating a graph here with an iGraph function, you need to pass down all the edges to it, and those edges are passed in the form of tuples. So basically, we need to get this text data here and create tuples from them. So the best way to do that is with the help of pandas library. So I'm going to import pandas as PD so that we can read this file and process the data easily. And then I'm going to create a data frame from it with pd.read csv, and inside this I'm going to pass the name of this file. So here comes my data frame, and you can look at the head of this data frame to see how it looks like. Now, if you look at this data frame, so there are a few problems with this. So first of all, it considers the first row as a header, and then the information is pretty much not in the way that we want it. So you see, we want edges from 1 to 2, 1 to 3, 2 to 3. So essentially we want two columns where this number 1 it comes in the first column, and this number 2 it comes in the second column. We don't want any headers, and rather we want to ignore the first two lines. So there are certain parameters that you can use here while importing this data. So first of all, you can say skip rows equals to 2. That means ignore the first two rows of this data set while importing it. And we do not want any header. So we are going to do header equals to none. Let's do this much and see what happens. And do we need to change something? So after doing this, let's again import this data set. Now what it is doing is it is getting everything. So first two rows are not there, but it is getting everything in like one column. So we don't want one column, we want two columns. So why it is coming as one column is because by default the separator that pd.read csv uses is a comma. So there is no comma in our file, it's a space separated pair of nodes. We can actually indicate our own separator here, which is supposed to be a space. And then let's do it. And we get the data in the format that we want. So there is column 0, which is having the first labels of the first vertex, basically first vertices, and here are the second vertices. Now we can use this data set to create edges. We can directly use a function which is available in igraph, which is I think, so I'm just checking here, I think read underscore tuple list, or I guess it is only tuple list. Maybe we can just check. So the idea is you create a graph, and to obtain this graph, you need to pass it a list of tuples. Now we need to see how can we get a list of tuples from this data frame first. So I'm going to remove this, and you can use this function called df.iter_tuples, and let's run it and see what it gives. So it provides you a map. So what you can do is to see exactly what is inside it. You can typecast it to list and see what happens. So it is telling you, so it's giving you a list of tuples where you have indices, and then it tells you what is the first vertex, what is the second vertex, again what is the first vertex, what's the second vertex. If this is confusing, this underscore 1 and underscore 2, I can try to make it simpler to see what's happening here. So what I'll do after I import this data frame, I'm going to name its columns as, so you see here the column names are 0 and 1. I'm actually going to name these columns name as source and target. So basically your edge is going from source to target. And since it's an undirected graph, from target to source also, but then it's just a naming convention. Instead of 0 and 1, I want source and target. And you see, so you get your source and target. And now let me, sorry, just created it by mistake. Yeah, let's again run this df.itertuples. So now I think it's better to look at. So you get index of each tuple, you get what is the source vertex and what is the target vertex. But the thing is, we do not want these indices and these names. So we only want a list of tuples. We can actually hide these indices and names by I think something like index equals to false and name equals to none. Let's see if that works. Yeah, correct. So you are basically saying that you do not want any indexing while you give out this list of tuples, and you don't want any names either. So when you do that, you get this entire Panda data frame as a list of tuples. Now this list of tuples you can directly pass it to your graph function. So I'm just going to store this list as, let's say, edge list. Instead of printing it, I'm going to store it as edge list, which I can then pass to the function. Now I can say g equals to graph dot, it is showing me some functions here. So it automatically shows you some functions. So tuple list is our function that makes it easy. And then you pass edge list here. So you create a graph from all these tuples. And we want one more thing here, which is we want this graph to be undirected. So you can set directed equals to false. And you can actually check, I think by default also it is false. So let's just run this and your graph is created. You can print your graph G to see what's happening. So when you print G, you see a few things here. So it's an I graph. U means it's an undirected graph, and means it's a named graph. So named graph means your vertices have some kinds of names, and then there are 34 vertices and 78 edges. Now, there is something peculiar about iGraph, that is, you see, when you look at your original file or when you look at your data frame, essentially your vertex numbers are starting from 1, 2, right? And then usually whenever you get any CSV file like this, it's not guaranteed that first of all these numbers they will be consecutive. It could be 100, 200, 3 also. It could be some string, some actual names like Neha and Nikhil also. So the point is all of these are considered as the names of the vertex. So let me show you what I mean. So as you can see here, there is an edge from vertex 1 to 2, 1 to 3 in our graph. Yeah, as you can see here. So you have edge from vertex 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. But what I want to show you is we can actually look at all the vertices of this graph with the help of this object g.vs. So g.vs actually shows you some kind of vertex sequence. And again, to look at all you can iterate through this vertex sequence, but then to look at what all is encoded inside it, it's always good to typecast it as list and it will show you what is happening. Now you see what's happening here. Your vertex, which is named as 1, that's actually 0 for iGraph, something which is 2, that is 1 for iGraph. So what iGraph does is it does an implicit indexing of every vertex, which always starts from 0. So you have to be careful about that, because whenever you report any kind of results or you visualize this graph, you have to be very sure that what you are looking at, are they the names of your vertices or are they the indices of your vertices. So in this case, the difference is only 1, but then this difference can be huge for some other graphs. We can talk about it as we go along. So the idea is you can look at all these vertices over here. Okay. So before proceeding further, let's look at how this graph looks like. So we saw how this karate club network looks like, and we saw a small visualization here on Google. So we would like to create something like this on our own. Come here, and what you can simply do is say ig.plotg. So iGraph has this plotting function which will plot this graph and show to you. And obviously it doesn't look that nice as the one that we see here, but we can get this graph to better shape with time. So I'll just hide it for some time. Now, there are few things that you can do with this graph. So first of all, you see this box, this white box in which this graph is shown is quite big. And control the size of this box with a parameter called bbox, bounding box, and you can give it a size So if I say 400, 400, so the exact units of this depend on your screen size, but essentially you are saying 400 units of width and 400 units of breadth, something like that. And when you run this, you see it actually decreases the size. You can decrease it further. So let's say 200, 200, and it will become all the more smaller. And now when this graph becomes smaller, you see it doesn't look very nice because vertices are also big. So you would want the smaller vertices. So we can do that with the help of another attribute, which is vertex size. And let's check out with the size of 5 what happens, right? If you want it to be a bit bigger, you can make it 10. Right? So this looks better than before. So this is how the graph looks like. Now, one thing that you do not see in this graph are the labels of the vertices. So as an example, sometimes you might want to identify some kind of nodes. You might want to say, okay, this node over here seems to be connected to a lot of other nodes, and it is always helpful if it was labeled with some numbers so that you could say, maybe node number 46 here is connected to a lot of other nodes and things like that. So what we are going to do here is, let us use the names of these vertices as their labels. You can say vertex underscore label equals true. So there are many ways of doing this. You can also give your own labels, or you can give a list here. But what is always better is, since we have this information, you can say g.vs name. What it does is, in your vertex sequence, every vertex has a name. So let me show you what happens when you do this. So if you say g.vs name, it actually gives out a list, and this list has the names of all your vertices. So essentially we are passing that list of names here. And if you run this again, you see all these labels, but again, they don't look nice. Their sizes are big. You can control their size with vertex label size equals to, again, let's try with a size of 5, and it is still big. So let's try true. Seems not to be working. Vertex underscore. mm, Okay, so it is vertex. And it doesn't show you an error, but there was that was wrong. So you see these vertex sizes, they have increased. We want to decrease them. So let me try 10. That is still big. So let's say 5. And this looks much better. If you want, you can increase both. Let's say slightly. So you can say vertex size to be 15, and let's say this to be 8. Now this looks slightly better than before. So this is how you can plot this graph. You can control for the colors of these nodes. So let's say you want every node to be of yellow color. So you can say vertex underscore color equals to yellow, right? And it shows everything in yellow color. So this is how a very, very basic visualization of Karate Club network looks like. Now, you can do certain things on it. So one thing, so two things that you can visualize and which are interesting is, maybe first is where you control the size of these nodes. So as of now, all of these nodes has a size of 15, but let's say you want to control the size of a node which should be let's say dependent on their degree is how many people they are connected to. So you can actually call this function called g.degree, which shows you the degrees of all the nodes. And as you can see, the degrees go from, I think, 1 to 17. So this is a list. If you want to see what values exactly are available, you can convert it to a set, and then it shows you there are values from 1 to 17. So we can use these values to control the size of these nodes. So what we can do is maybe we can make vertex size to be mm, I'm going to use list comprehension here. Let me say I plus still understand what I'm doing. So I'm saying I by 10, 15 plus I by 10 for I in G dot degree. So basically you take the degree of each node and then you divide that by 10 and add 15 to that. So that should be the vertex size. And if you run this, there is a size difference, but I think that's not like very properly visible in here. So let's try dividing it by 5 and see. Not that good. So let's take it exactly I and see what happens. Right, so I'm saying let's say vertex underscore size equals to simply g dot degree. And then we can see what kind of modifications we need to do. Now you see some of the vertices are very big, some of them are very small. So that's why let's say if we could divide that by 2 so that the vertices which are big they also become small, but those which were small they became more small. So let's say 5 plus this. Yeah, so this is still better. And I think as we increase it, the distinction in size becomes lesser, but you can see that some vertices are bigger and some are smaller. So you can do that. Then another thing for which this karate club is very popular is people like to apply community detection to it. So community detection means two dense subgroups which you can see are densely connected with each other as compared to rest of the network. So as an example, if you see here, these seem to be two different communities. There are some other visualizations available for karate network. So so it depends on which community detection algorithm do you use. Some algorithms gives you two clusters, some algorithms gives you four clusters. Let me see if I can show you. Karate club community detection. Oh, I don't see some very impressive networks here. So let's do that on our own. Come back here. Right? And now what I want to do is apply a community detection algorithm on my graph, which spits out some kind of cluster. So clusters means densely connected nodes or group of people. Say G dot plus G dot community. And as soon as you write community, it starts showing you a lot of algorithms to do that. So I'm going to use optimal modularity. I use this optimal modularity because this function, it will actually run all the community detection algorithms available with iGraph and give you the best one. Since it's a small graph, we can do that. If you do that for bigger graphs, that might take a lot of time. So since it's a graph with 34 nodes, it was easy to do. And you get some clusters here. So let's see what are these clusters. So it's again an object. So let's try converting it to a list and see what's happening. So you see it shows you the clusters in the graph. So this actually shows you four communities. And how do we know whether it's a good detection or not? So whether these results are good or not. So there are two ways to do that. So one is you can look at something called modularity. I'm not going into the technical details, but what this function does is it gives you, no, it's not a function here, an attribute. So what it does is it gives you a value from -1 to +1, showing how good this result is. So you get a value of close to zero point 0.4, which is decent enough, right? Which is slightly on the positive side, showing you that yes, there are significant communities in this graph. Now, what we would want to do is we would want to color the nodes of this graph based on these communities. So, though there can be shortcuts for that, you can take help of an LLM, but I'm going to do it in a very raw way. I'm going to iterate over all of these clusters and allocate colors to nodes. So what we want is, as you see here, I want a list of colors, actually a list of 34 colors, where the first value. So I want a list of colors, something like this. So let's say red, comma blue, comma red, right? So something like this, and there will be 34 colors here, one for each node. But then the point is these colors should be dependent on what you got here. Basically, all these nodes should have the same color, and then all of these nodes should have the same color, all of these nodes should have the same color, so on and so forth. I'm going to make a color list which is initially empty, and then I'm going to iterate over this. So let's say for I in range, there's a reason why I'm iterating like this and not doing it with the for each loop. You'll understand that soon. For I in range 0 to this, you show me what is clusters of I, and when you run this, it gives you all of these lists one by one. Now I'm going to make another list of available colors. I need 4 colors, so let me take pink, cyan, um, yellow, and so I'm just trying to choose some lighter colors here so that things are nicely visible. And let's say orange. So these are the 4 colors that we are going to use. Now what I want is every node in this cluster. So every node in this ith cluster should have the ith color from here. So I'm going to iterate one more time here for node in clusters I. So it iterates through all of these values for the very first cluster, this for the next one, so on and so forth. I'm going to say G dot, so you can append it actually to the color list. So I'm going to say color list dot, no, that might create some problem. So I'm not going to use this. What I'm going to do is to each node in the graph, G dot node, and this particular node that you sorry g dot vs, and this particular node that you just found, its color, I am setting it as clusters I. That's all. So now all of your nodes have got colors, and you needn't even pass anything here. You can just run this code, and so I'm going to remove this default yellow here and then run it again. Gives me some error. Let me check again. So come in here. So let's look at what this looks like. G dot vs color. Okay, I've done some mistake here. So it should not be clusters of I here, my bad. It should be available colors of I. So these are the available colors for cluster I. You give it a color which is available colors of I. So let me run this and this again, right? So now it shows you 4 different communities, and I guess we can sort of make out that, well, yes, there are 4 different communities, and we'll see less connections across communities. So that is some very, very basic analysis that you can do by importing in the Karate network data set. If you would like to do something more specific or something else, you can mention those in the comments and maybe I can show you next time.